Okay, can you hear me okay? Okay, those were very good presentations, hard to step in. I was going to brave it out there, but I better hide behind the podium for now. So I want to talk to you about the new space race, and a good place to start is talking about the previous space race. So this was a race between the two superpowers at the time, the United States of America and the Soviet Union, who competed to send satellites, animals, and eventually people into outer space. All of this while using those rockets to intimidate each other with the prospect of a nuclear war. Now, this time between 1957 and 1969 brought about a number of very important milestones for humanity. We had the first satellite placed in orbit, that was Sputnik. Then we had the first human in orbit, followed by the first American in orbit a year later, and then the first woman in space in 1963. And there were many more milestones, but perhaps one that is iconic is in 1969, the landing of Apollo 11 on the moon and the first human presence on the moon. And from this point forward, the story becomes very interesting from a geotechnical standpoint. It turns out that since Apollo 11, every Apollo mission through Apollo 17 brought back lunar rock and regolith samples back to Earth, except, of course, Apollo 13, which brought back Tom Hanks. What is nice about that is, so we had about 2,200 total samples brought back with a combined weight of 381 kilograms. And that is an interesting sum because we can use that to try to estimate the cost of sending something from Earth to the moon during the Apollo time. So it turns out that in 2003, NASA was sort of forced to put a price tag on those lunar samples. And it was in the middle of a criminal case involving a number of interns at Johnson Space Center who had stolen a safe full of lunar materials. And so the federal government had to put a price tag on that, and they came up with a number of $50,000 per gram based on the cost of recovering those samples and bringing them back to Earth. So if we assume that $50,000 per gram is a round-trip fare to the moon, then one-way ticket will be half of it, 25,000 grams, and if I multiply that by 1,000, I get a total cost of shipping something to the moon during the Apollo days of about $25 million per kilogram. And that is a lot of money at the time. And so it's no wonder the Russians weren't able to keep up with the space program. They ran out of money before they could put boots on the moon, so to speak. Now, the space race is still going on. This continues, but the players have changed. It's no longer a race between the superpowers. It's now a race between the super rich. And so that shift from government to industry comes with some advantages. One of those advantages clearly is competition. So the cost of shipping something to the lunar surface has come down dramatically to the tune of around $25,000 per kilogram. Now, that's very good, but it's still quite expensive. Now, if I were to summarize the old space race, I will say it was a race to get us there. The new space race has a different objective. The objective is to keep us there longer. So with the Artemis missions, NASA is going to land the first woman and the first person of color on the moon. This is going to be a very collaborative effort that is going to bring together commercial and international partners in an effort to, for the first time in history, develop a permanent human presence on the moon. Part of the plan here is that we can use now the moon as a laboratory to test the technologies that we will eventually need for the next big step in the space exploration, which is going to be sending astronauts to Mars. Now, NASA, through the Lunar Surface Innovation Initiative, has identified a number of target capabilities that are going to be necessary for us to do that. And so I'm going to highlight some of those here. Clearly, if we're going to be maintaining a presence in the moon, we're going to have to utilize those lunar resources. We cannot just ship everything from Earth there. And one thing that is very interesting is that this new race is more about civil engineering than you think. We want to have infrastructure that will support a human presence, a permanent human presence on the moon. And the resource that we have available to us is rock and dirt. And we know quite a bit about that. So it's a very geotechnical engineering problem. Now, one of the issues that we have in doing so is the extreme environment that we face on the moon. The lunar surface is a harsh environment. Professor Mitchell, in his Geo-PIT talk in 2019, described the challenges that we face there. So there is no atmosphere on the moon. So it's essentially an ultra-high vacuum at 10 to the minus 12 torricellis. That means that you have very little protection against radiation and micrometeorites. The temperature swings along the equator are very harsh. You go from negative 153 degrees in the cold nights to over 107 degrees during the days. And if you go to the South Pole, where we're planning to send those Artemis missions, the things get even worse. Temperatures go down to about negative 250 degrees in those permanently shaded regions of the moon, and that is getting very close to absolute zero, so it is extremely cold there. Now, that is scary, but the thing that I am most concerned with is the low gravity environment. So the moon is at about 1/6 of the gravity of Earth, and that makes it complicated for equipment that has been developed on Earth to conduct air work to work properly there. So I want you to think about an excavator. And the thought that comes to mind is going to be an articulated arm with a bucket at the end that is going to collect soil, right? And when you go to the moon, that is a very inefficient way of doing it. So a lunar excavator looks like that. That is a RACER prototype, which is an excavator developed for lunar regolith out of NASA's SWAMWorks in Kennedy Space Center. So we're going to have to question the equipment we have and come up with novel ways of doing that. I want to develop, and this is going to be a segue into the bio-inspired portion of the talk, talk about subsurface exploration. So that's been identified as one of the target capabilities that we're going to be needing. And we know quite a bit about subsurface exploration. In that chart, we had the dynamic duo, CPT and SPT. And I'm going to talk a little bit about that CPT. Well, a CPT truck of about 20 tons can go about 30 meters in depth. So if I take that depth and divide it by the mass of the truck, that comes to about 1.5 millimeters per kilogram. And that can be thought as an index of how effective that design is at leveraging its mass to penetrate into the ground. Now, the cost of shipping that truck to the moon, based on the $25,000 per kilogram, is about $500 million, which is a little bit higher than the price tag of the truck, so a bit expensive. What can we do to come up with a design that will be more effective and lightweight? And so what we had turned to is the earthworms. This is a chart of the different earthworm species according to functional groups, and one that I concentrate on is the anisic worms that tend to create burrows that are vertical, and they can go down to depths of about 2 meters. So a worm weighs about 50 grams, and it has a depth range of about 2 meters. So when I take that ratio again, that is 40 millimeters per kilogram. And when you compare that to a CPT, you can realize that they're much more effective at using their mass to access the subsurface. And the shipping cost is something that we can afford to send to the moon. I don't advocate to send worms to the moon, but it's going to be certainly cheaper. Now, I will warn you of the danger of underestimating the worm. The worms may not look very strong, but they have survived 3 out of the 5 mass extinction events. We can date worms back to about 280 million years back. So they lived through the Permian extinction, which is the Great Dying. It wiped out a huge number of species on Earth, and it survived the extinction that took out the dinosaurs. So if you're looking for a stone-cold killer, don't look at the T-Rex, look at the worm with a different eye. Oh, I should have warned you before I jumped here. The outcome of bio-inspired work depends on 2 organisms. The first organism is the source of the inspiration, in this case the worm, and the second organism is the organism being inspired, in this case the geotechnical engineer. So when you task a geotechnical engineer with being inspired by a worm, he comes up with a worm-looking cone. And so what you see in that cone is a flexible membrane that allows the cone to expand and contract as it moves within the subsurface. And in deploying this earthworm-inspired penetration strategy, what we have found is that we can decrease substantially the penetration resistance to this device, to the tune of about, when you take a look at translating that penetration resistance into a mass that is required to anchor the device at the surface, let's say, we can reduce that mass at the surface by about 70%. So not bad for sticking a balloon in a cone. Some of the other things that we have found is that that comes at the cost of an increase in the penetration energy. So enacting that inflation and deflation of that membrane requires energy to do so, and so that increases the energy consumption. However, when you take a look at peak power demand, which is the main constraint when you look at space exploration, it comes very well within the range of power that is available to rovers such as those sent to Mars and to the Moon. And our goal is not just to stop there with that modification to a cone, but to develop a device that will separate us from the surface. So where we no longer need to have a surface ground anchor to go down. And so this is a prototype of one of the devices that we're working in, where we eliminate the surface equipment completely, and the entire device moves underground. And I was so scared about the timeline that I may have gone too quick over the presentation, but that's all I had. Thank you very much.